Okay, this is the first video for Chapter 4. Chapter 4 is titled Three Major Classes of Chemical Reactions. What's interesting about this chapter, I think, is they don't really tell you what the three classes are. In fact, you really have to kind of dig around for it. It's not until Chapter 4 or Section 4.2 do they even list the three major types of reactions. So I'm actually going to do that right here. I'm going to kind of spell them out, and I'm actually going to talk quite a bit about water, and you'll see why in a second. So the three major types of reactions. Why do I never have my pen when I start these videos? There we go. Are precipitation reactions. Precipitation. Okay. Acid-base. And oxidation reduction. Also kind of abbreviated as redox, which is reduction oxidation, kind of a shorthand. Okay. Now, the first two of these reaction types will be covered in 4A. At least I think that's how your professor divided it. And the oxidation reduction will be 4B. So I'm going to focus on this video kind of an intro for the first two, for precipitation and acid-base. And both of those reaction types are, let's say, water is very important for both those reaction types because an awful lot of, or the common examples of these two types of reactions take place in the presence of water. Okay, that's also known as aqueous solutions. I think we have mentioned that before. So I'm going to talk a little bit about water here now and why water is so important, or well, I'm going to try to convey why water, or some of the water's properties are important in these two types of reactions. Okay, and then 4B we'll talk about oxidation reduction, and water is not as central, it doesn't play a central role in that and those types of reactions. So so again, that's why I'm focusing on water right now. Okay, now water. Let me draw you water as I struggle to find my eraser. Okay. And I think I drew this before, and water is a pretty simple little molecule. You see when you draw it, it looks pretty simple. It's got an oxygen and two hydrogens. And remember, we kind of talked about electrons before, and these little dashes that I'm drawing are really a pair of electrons. One comes from the oxygen, and the other is the hydrogen, is the electron that hydrogen donates. And oxygen itself has 1, 2, 3, 4 more electrons. So oxygen brings to the table these 6, 1, 2, 3, 4, 5, 6, and each of the hydrogen brings one electron to the party, to this compound. Now, a couple of things I want to mention about this. We still haven't really talked about why 8 electrons is such an important number, but I'm coming to that. But if you can see from oxygen's perspective, it's actually kind of surrounded by 8 electrons. 8 is the correct number, is the ideal number. That's kind of like the noble gas sort of number, and that's why oxygen likes to have 8 around it. You'll see that in a lot of other compounds that's also the case. Even like, well, I'm not going to draw it, but methane has the same sort of arrangement. Now I'll draw it, but I'm not going to dwell on it. Methane, for example, the carbon is sharing an electron from each of the hydrogens, and carbon brings 4 to the table. That adds up to 8 as well. So now, what's interesting about water, though, and I'm going to actually now draw back the lines. Is that it forms kind of a bent molecule. I mean, down at the molecular level, it really is kind of angled like this, and the molecule itself is kind of has some charges. This side, the bottom side, the oxygen side, has kind of a negative bent because oxygen is kind of inherently negative. If you think about it, if oxygen were to kind of steal, to steal an electron entirely here, it would become negatively charged, and the H would go off without an electron and be positively charged, right? So, and down there, as water is kind of flexing and doing all its doing all this bending, it actually kind of does that. And you'll see that in a second when we talk about acid-base reactions. So the molecule itself kind of has a negative side and and the H's are kind of the positive side. What that means is that it's open to helping other compounds, other molecules, to kind of divide along those lines. And I'll show you kind of a quick example of that. Is again, if you think again, this is sort of the negative side, and this is sort of the positive side of the molecule. If something like sodium chloride came around, the sodium, which is kind of positive, and basically this could easily divide into a positive side, sodium, without its electron, and a chlorine side with the sodium's electron. And the chlorine would be happily associate itself with the positive hydrogens, and the sodium would be happy to associate with the negative side, the oxygen. So essentially, water acts as a way of splitting a sodium chloride molecule. And again, it's part of a solid, but splitting out a sodium and a chloride from a crystal of salt, and splitting it such that the chlorine associates with the plus side and the sodium associates with the minus side of the water. And of course, in an aqueous solution, you got water. It's three-dimensional, of course, not this little two-dimensional picture. There's waters kind of everywhere, and so the sodium can actually associate itself with other waters up in the third dimension, or even in or even in the second dimension, like this. Right. So essentially, think of this as that water, the polar nature of water, the fact that water is charged or has a polar, has a plus and a negative, a positive and negative side of itself, allows itself to insert itself or to surround other ions, causing them to what we call dissolve, meaning they go from a solid like NaCl to a more stable electrically situation, which is dissolved in the water. And again, water is a really nice, really good liquid for this sort of thing. Other liquids that aren't as polar as this, like alcohol, for example, or or oil or butane or something like that, those liquids do not do as good a job in dissolving ionic compounds like sodium chloride because they don't really have this inherent electrical nature in itself. All right, now there's one other thing I want to point, and I'm going to talk more about ionic stuff in the next video. The other thing I kind of want to talk about water in general is, and this is kind of a general comment about all these compounds that we kind of draw statically as looking like this, is that it isn't really, down at the molecular level, water molecules aren't just exactly looking like this all the time. For example, when you put it with a bunch of water molecules, you might find that this water molecule actually has another hydrogen that it got from another water that kind of gave it up. So it's like, here's a water that used to have this hydrogen, but at least for a moment this disappears, and the electron goes with the oxygen so that this thing becomes negatively charged, and the hydrogen attaches itself to this oxygen, and this whole thing becomes positively charged. And you'll find in solution that this sort of thing happens kind of along the lines of what we had said with ionic bonding, is that in an ionic bonding case, instead of sharing electrons, one side just kind of borrows the electron from the other, and then they become charged objects, but larger ones. This is similar to what happens even in liquid water. Is in liquid water you'll have a mixture of, even though you can easily see that this H could come back to this OH and become regular water again. They tend to kind of split in part and actually, for moments anyway, exist in a state that's a bit separate. Now in this world, this object that I've drawn a circle around is actually a larger positively charged object, and this other one is a larger negatively charged object, as opposed to kind of what we were talking about when looking at a covalent bond between oxygen and hydrogen. Okay, we'll build on this further because this is kind of the essence of acid-base as well. But I kind of wanted to show you that water has some interesting properties, and actually, as it pertains to dissolving ionic compounds or even dissolving non-ionic compounds, which we'll cover in the next video. And it also has some interesting properties in its own right, where it isn't it doesn't solely exist as nothing but H2O molecules. It's kind of a mixture of H2O mostly, but also these other two ions that I'm showing here, which I'll talk about under acid base. Okay, that's it for this one.